All right. Very good morning, good afternoon, and good evening, everyone. And welcome to the first plenary session of the virtual FRB 2021 conference. I'm Shivani Bhandari, and I work as a postdoctoral research fellow in CSRO based in Sydney. And today I will be chairing the session. Well, I think all FRBs are special and unique in their own way, but what story do they tell us together as a population, especially now since we have hundreds of FRBs published? And we are going to explore that in this session of populations. We have some really interesting talks lined up, and the speakers will be delivering their talks live. So it's going to be a really interesting session. Clancy James from ICRAR Curtin is going to kick things off and tell us about the FRB population, selection effects, biases, and the Macquart relation. Clancy, I'll give you a 3-minute warning, and yeah, all yours.
Okay, let me just get the share screen up and maximize. So first of all, it's an honor to actually be the first speaker at this conference, and thanks to the organizers for getting it ready. You know, this is probably the highlight of the year as far as fast radio bursts are concerned. And let me also begin by saying thanks to, my co-conspirators in the craft collaboration. In particular, you see the names there, Professor X, the late JP, Freya, Keith, and Alex in particular this work, but the whole craft team. All right, so let's begin. So as Shivani mentioned, there's a lot of things you can talk about regarding fast radio bursts. I'm going to be concentrating on the population modeling, right? Are there more or less FRBs at high or low redshift, high or low frequencies? How many are there? Bright versus dim ones, right? I don't want to think of these as their own special little snowflakes, as Shivani or Ryan might say, right? I'm going to try ignoring topics number 2 and 3. I'm also not going to be talking about topic number 4, FRB cosmology, but what I'm going to be talking about is extremely relevant for that. Because if you have biases in population modeling, we'll see that this is inextricably linked with fast radio bursts. Okay, so what we want to do is we want to get at the true FRB population over here, right? But then this comes to us through this annoying thing called a radio telescope, right? Which is an imperfect instrument. It's not a massless, frictionless pulley. And this introduces observational biases, right? Due to our detection methods. And it means that we don't see the full true population. And it might mean that many possible truths match to what we see, right? So the correct approach, right? It's just the correct approach is to model all these effects, vary the unknowns, and fit to the observables. Right, and essentially this is what's advocated by Liam Connor in this paper. And as far as I'm aware, it was essentially first instrumented by Ray Lau, right, who really did this comprehensive approach. And I'm going to try to convince you that's what you need to do. So I'm not going to go into the full details of this, right? I just want to give you an example of what you might want to do when you want to calculate the rate of fast radio bursts detected by an experiment. Well, you've got some expected number of bursts, which is the time that it's been observing times the expected rate. That rate is, well, you've got to integrate over the redshift of the universe, right? Here's your cosmology here, and Mawson's going to be telling you later in the session that this might be wrong. You've got to do the FRB population, which may or may not evolve in some way with redshift in a complicated way. You've then got the DM distribution of the universe, right? The halos around galaxies themselves, and fluctuations in the intergalactic medium, plus, of course, the ISM and our own halo, right? You've got to integrate that. And there's a certain probability of getting a DM for any given redshift. You've got your telescope beam shape, right? More sensitivity in the center, less at the edges. You have different, well, I've called it burst width effects, but burst shape effects, right? Not all bursts look the same, and their widths as a function of time affect how you detect them. And you've got some intrinsic luminosity function, right? So let's imagine your energy threshold here, which is a function of where you are on the beam, what redshift you are, the properties of the burst, and its dispersion measure governs your energy threshold. Well, how many FRBs are there above that threshold, right? Now, this talk, I'll be assuming the homogeneous universe. So I'll leave the rest of the discussion of this to Mawson. Now, you can do analogous calculations to get the probability of getting a certain dispersion measure or redshift, a probability of getting some signal to noise ratio, right? A probability of observing a width, etc. Now, for the moment, I'll be ignoring repetition, right? And what that really means is your probability of getting n bursts is a Poisson distribution, right? Once repeaters get in there, then these are clearly correlated in all sorts of horrific ways that I'm going to try to push to another session and leave the wonderfully talented other people at this conference to talk about in more detail. But what I will point out is that when we're talking about biases and observations, the worst biases of all sometimes are us, right? We're astronomers. We have control of telescopes and we like to point them at interesting things, right? And what that means is that the future observations are based on past observations, which is a horrific statistical problem, right? Now, what I want to really make a strong statement here is that the only FRB survey to ever detect a repeating FRB is CHIME, right? All others have been detected as repeaters in targeted follow-up surveys, right? Until there was a targeted follow-up, all other repeaters were once-off bursts. I mean, maybe we're going to find out something different at this conference, but I'm going to be talking in particular about the ASKAP and PARC samples, right? And each of these in the surveys, right, not targeted follow-ups, but surveys, only detected bursts as once-offs, right? So in general, we need to remember that repetition is going to matter when you've got long dwell times with a sensitive telescope in a single sky position. And we'll get back to this one. Okay, the other nuance and complicating annoyance I want to talk about is spectral behaviour, right? So there was this result from Jean-Pierre Macquart et al., who essentially modelled FRBs as having a spectrum, right? You know, the fluence is some frequency to the power of alpha, and modelled this alpha as minus 1.5 plus or minus about 0.3, right? And that gives you a K correction to your energy as a function of fluence, right? And the idea was that, okay, craft FRBs are mostly broadband with, you know, fluctuating spectra on top of that. Okay, sure. However, I would argue that if you think this FRB, you know, detected by Pragya, over about 50 megahertz out of 4 gigahertz has a spectral index, you are patently insane, right? And CHIME has recently told us that, sure, some FRBs are broadband, others are very narrow band and have complex structure. So an alternative extreme from this nice broadband behavior is to say that FRBs are narrowband with a frequency dependent rate, right? So the rate is proportional to frequency to the alpha. And if you interpret the result of Macquart et al. In terms of a frequency dependent rate, you get an alpha of minus 0.65 for reasons I could extrapolate to later. So the truth is a mixture of these two extremes. And so in that case, well, let's just model both and see what the difference is, right? But if you're modeling FRB surveys, you've got to consider the influence of your interpretation of what a spectral index is. Okay, so we did this modeling data from ASKAP and PARCs, right? Unlocalized and localized FRBs. You know, these are the respective beam shapes. And I want to point out here that when you're modeling the ASKAP beam shape, a Gaussian is not good enough. The beam overlap is important. And if you model these beams as independent Gaussians, you're going to get significant biases. For PARCs, it's close enough, right? So we were fitting the number of FRBs observed, the DM and redshift, and the signal to noise of these, right? So you can fit all these relations and they all give you useful information. And all of these observations were at L-band. So on the one hand, it mitigates spectral uncertainties. On the other hand, you can't really model them. So this meant we had some parameter degeneracy, right? So if you're fitting the FRB population and you say, okay, let's try to model the number of high Z FRBs, right? Let's imagine we want to reduce that. Well, you can do that by having slow source evolution. There's just not many FRBs there. You can have it with a significant K correction, right? Alpha is very negative. You can have it by having a low Emax. You just can't see many FRBs out there, right? And from the modeling, it's difficult to tell the difference. So if you look at these two-dimensional fit functions of Emax and alpha and N and alpha, right? There's these broad degeneracies you get there. So what I was essentially doing is you want to apply this, prior as such from Macquart et al. There's another discussion as to how applicable that is, but I don't have time to go into that, but I would like to discuss it offline. Okay, so first results on population evolution. Let's model the FRB population as a function of redshift using McDowell and Dickerson, and then let's smoothly vary it by N, right? So N is 0, no population evolution, N equals 1 star formation rate, N equals 2 faster. And this is what you get. Now, this is this spectral index interpretation. This is this rate interpretation. This blue is with basically a uniform prior on alpha, right? Essentially no prior. And in yellow is with the Gaussian prior. And okay, you can look at the results, right? But what I really want to point out is that we exclude, in all cases, N equals 0 at better than 95% significance, right? However, if we're here, except if we're in the rate interpretation and we have no prior on alpha, then we can't. That's the only case, right? So it's strong evidence that the FRB population is evolving. Right now, okay, that might not be unexpected, right? Evolves with redshift. It's consistent with the star formation rate, but we don't have the resolving power yet to tell the difference between, let's say, a delayed merger model, for instance, something that's delayed with respect to SFR. As far as maximum energy goes, well, nothing special here. It's a number, right? The main point is that we have strong constraints that the maximum energy must be more than about 10 to the 41.4 ergs because we've seen some localized FRBs with that energy, right? I do want to point out that if you look at the results of Lau et al., where L star here, it's in different units, right? It was luminosity, so per second. So if you scale it to a millisecond, the results of Ray Lau et al. Fall about here. And the reason why we're sort of consistent with the top end of Ray's estimates, but not the bottom, is because Ray didn't have access to the localized FRBs in modeling, which have a very sharp cutoff there. All right. So if you're a theorist and you care about Emax, as in can your model reproduce it, here's some updated estimates. Now, what about the luminosity index, gamma, right? So what we're doing is we're doing a model where the probability of getting an energy above your threshold energy goes to the power of gamma, essentially, right? That's the cumulative source luminosity function. Well, there's basically three magic regimes, right? If gamma is less than minus 1.5, all your FRBs should be in the nearby universe and it's dominated by E min. We clearly don't see that. If it's flat, gamma is less than minus 1, FRB should be seen near Emax in the distant universe. And if you're in an intermediate range of minus 1.5 and minus 1, FRB should be spread out, but have an excess in the local universe. Well, the best fits don't exclude the steep range, but they're really in this intermediate range. And one of the telltale signs of that, I think, is having some FRBs that we're finding in the very small nearby volume, right? Like this FRB in M81 that was found by CHIME. Which, by the way, this wasn't part of the model. So this is kind of cool that CHIME got that. Now, there is a little bit of tension in this, right? So if we look at fits, here's redshift and the number of FRBs from the localized ASKAP sample. And you'll see that no matter what I do, right? If I've got the best fit, which is in orange, this is green with no evolution, clearly doesn't suit. But if I try to put in a minimum energy, right? And gray is different confidence intervals, no matter what I do, there's a deficit of near universe FRBs in the sample. So I would have expected there to be some very nearby localized ASKAP FRBs, and there aren't. And one explanation, as I'm sure will be talked about a bit more by D. Lee from FAST, although it was talked about at last year's FRB, is that maybe, there's a decrease in the luminosity function, right? But I will point out this deficit's only at a 7% level of significance, right? So there's some tension, but it's not too bad. All right, I will mention this, right? There's also the effects of repetition, which I said I would get back to. So I'm keeping my promise. In the distant universe, the number of bursts per repeater is generally less than 1, right? Whatever distance is. Because you've got a large volume and many repeaters, so the total burst population behaves as a Poisson distribution. In the nearby universe, the number of expected bursts per repeater becomes large, but you're only probing a small volume, so the probability of having a repeater in the near universe is small. So it's highly non-Poissonian.
And so 3 minutes left.
Excellent. Thanks, Shivani. And so what you expect is most of the time see a deficit in the nearby universe, but sometimes see a large near universe excess, right? So there's some hints of this in the data and also from FAST and a PhD student here, Wayne Arcus, so I don't think is presenting this, but has been analyzing that. Okay, going to skip host galaxy DM, updated numbers on that, nothing much to see here. All right, let's talk about the Macquart relation because I said I would. Here it is, JP's paper, and look, it's beautiful. Expected baryon density of the universe, localized FRBs, scattering around that. Great. This is a wonderful demonstration of the magical power of drawing a straight line. Let's turn this on its side. Now we have DM and redshift. Let's look. We've seen a DM with an extragalactic contribution of, let's say, 300. What's its redshift, right? What's the probability of its redshift given we've observed a DM? 0.1, 0.3, 0.4, right? This is not a one-to-one relation, okay? And it gets even worse because the model predicts that, okay, you get this here's the Macquart relation in blue here, DM and redshift, and this now includes a host galaxy contribution here, right? Which is why you get this excess there. And you see most FRBs are predicted to be above the line, but above a certain DM, and this is for the ASKAP incoherent sum observations, it turns over and you expect your FRBs to be closer with high DM. Why? Why is there this insanity? Well, the reason is that if you're on the one-to-one DMZ line, if you've got some maximum FRB energy, means you've got some maximum FRB redshift, which gives you a maximum DM along this line, right? And here's the probability of observing dm and z is the joint probability distribution here. But when your z is less than z max, right, when you're closer, you can still have dm greater than this supposed dm max because of, passing through some galactic halo. So if you then see a dm above dm max, it must have come from the nearer universe, right? And the details of exactly how this works depends on your other modeling functions. Here's some systematic effects. But maybe this is why CHIME is seeing a DM 800 correlate with Z.4 galaxies. Okay, so conclusions, do your modeling correctly. It's difficult, it's annoying, it's horrible to do, but you've just got to do it, right? And you've got to do your modeling correctly. These are the 3 key takeaways, right? What I want to do is concentrate on my wish list, which is CHIME's done an excellent job of modeling their selection function. It'd be lovely to publish it as a nice NumPy sort of some routine, right? Love to see more FRBs from FAST, probing the distant universe. And we've got an ASKAP FRB that we haven't localized yet with this DM. I'm predicting it's going to have a redshift of 0.8. Please hold me to that. And finally, sure, we're talking about science, but our Earth is in trouble, right? Global warming's a thing and something has to change. And nobody is going to keep funding astronomy if the world is in crisis. So we do impact it through supercomputing and travel. Thank you for making this a virtual conference, even if it was forced. And please help advocate for climate action, right? Astronomers for Planet Earth is a great forum for that. So I'll stop there and thank you very much.
Thanks, Clancy. If we have questions for Clancy, please post them on the Q&A functionality of Zoom.
I assume you'll monitor that, Shivani?
Yes, yes.
Well, I can certainly get back to that later anyway, if I should stop sharing my screen and let the next presenter get up.
So you still have time for questions. So the whole session is for 20 minutes, so 15 plus 5 minutes of questions.
Mm-hmm.
No questions yet.
I just forget the Shumdo is vastly over time.
No, it was just in time. Oh, okay. So we have a question from Emily. She's saying, besides CHIME and ASKAP, what could other telescopes be doing to help with answering these questions?
All right. So first of all, that's a difficult one. I think that there's a good case for looking for near universe FRBs, right? I think experiments like STARE-2, which are really focusing on the galactic population, it'd be good to also probe the very nearby universe to be able to like see how many close things there are, right? The very low energy part of the population. I also think that we should keep making sure that we do large FRB surveys, right? And doing commensurate things. I think that once we get to the regime of too many telescopes only following up our known repeaters, then we're going to be into a biased example where, it'll even get to the stage where people are only following up repeating FRBs during their known active periods, right? And if people only do that, then we'll only get bursts during their active periods and we'll never really be probing even when they are inactive. So I think that we really need to, and this is a broad discussion topic, it'd be really good to resolve what's going on with repeaters, right, as part of a broad population. But other than that, I really think that probing the distant universe with FAST and getting the damn SKA built, right, that'd be great. Let's focus on that perhaps.
We have another question from Zoavar, and they are asking, so what's the reason CHIME as a survey has seen repeaters, but others haven't?
It's because they've got a good sensitivity and a huge field of view. It's that simple. They stare at the sky pretty much all the time. And yeah, very broad sensitivity, good, very broad field of view, good sensitivity, right? It's that simple. I mean, it's not simple to build the instrument, right? Just ask anyone from CHIME. It's a fantastic piece of work, but yeah, that's basically it.
We have another one from Ron, who's asking, what is more useful to resolve degeneracy, more field of view or more sensitivity?
That is excellent. I would say that we need both. I think that we absolutely want the sensitivity, right? We would love the sensitivity to be able to probe the redshift 2 to 3 region, right? At the moment, my model says that most FRBs from parts are less than redshift of 1, right? And even from fast, they're mostly less than redshift of 1 to 1.5. We really need to first get sensitivity where we could be seeing and should be seeing FRBs from redshift 2 to 3 to really see, if it does have the kind of behavior that the star formation rate does, right? Where there's a downturn after redshift of 2. Once you get that sensitivity, then concentrate on increasing the effective area, I think.
We have another one from Ray, who's saying, in terms of selection biases, is it possible to synthesize both the blind surveys and repeater monitoring to obtain a comprehensive understanding of the whole FRB population?
It is, but it's a little bit difficult. So we've done some other work where you can sort of say, okay, given we've already seen one burst from a repeater, right? We know, given we've seen one burst from an FRB, we know there's an FRB there. Okay, we accept that bias. Now let's stare at it with another telescope for however long you want. What's the probability that it has this repetition property? Or rather, what's the probability that we did or didn't see bursts, right? Given supposed repetition properties for that. You know, and we've been doing that with parks where, in particular, FRB 17, 10, 20, which Freya North Hickey is going to be talking about this conference, its host galaxy is only 40 megaparsecs away, and we've looked at it with hundreds of hours, right? And we haven't seen any repetitions, which tells you either it's a once-off event, or it tells you that it's some extremely old object that repeats, you know, once in a blue moon. But it's very difficult putting that together. And honestly, I think it's up to the sophistication of the model / the sophistication of the people doing the modeling. But since Ray, I've already called you out as being a good modeler, let's get together and work out how to do this.
Awesome. I think we are running out of time. So now Ryan and Brian, if you can post your questions on Slack, that will be great, and we can take it offline. So our next speaker is Nidhi Saini, and she'll be talking about, are there two distinct populations of FRBs? And she's from University of Delhi. Nidhi, all yours.
Yeah, thank you, Shivani. Let me just share the screen. It's fine, I guess.
Yes.
Okay. Good morning, everyone. My name is Nidhi Saini, and this work is done with Professor Patrick Dasgupta. So let me just start. So everyone now knows what are FRBs. They are just high intensity millisecond duration of radio pulses. They have been detected just a decade ago, and now they are making noise everywhere, right? So their peak flux density is, so these values are taken from the catalog, is ranging from 0.04 to 600 Jansky at a given frequency of 400 megahertz to 2 gigahertz. And the typical dispersion measure is found to be very high, which is ranging from 100 to 2500 parsec per cubic centimeter, which gives you an idea about their distance. Or distance of the source to the FRB. So they are found to be extragalactic, assuming assuming the model for electron density for Milky Way, and obviously the value of dispersion measure for the given line of sight is supposed to be very high for FRBs to encounter the Milky Way part only. Now the brightness temperature is also very high, which is around which is greater than 10 to the power 35 Kelvin, which gives you an idea about the coherent emission of the source at the source for the FRBs. And the rate is expected to be 10 to the power 4 to 10 to the power 5 giga per cubic gigaparsec per year. And now this study that I'm going to show you is based on 140 FRBs with 20 repeaters. Okay, so just a very simple histogram for fluence gives you a bimodality in fluence. Obviously, the every FRB is detected at different frequencies. So just to putting every FRB on the equal footing, what we have done is we have scaled down the fluence to 1 gigahertz. And the alpha is taken from this study here, Macquart et al. 2018, which is minus 1.6. You can see that there is a dip which explains the bimodality. Now we have taken different values of alpha, and this dip is consistent with different values of alpha. So which gives you a hint that there might be a there might be two kind of FRBs or bimodality, obviously bimodality in the population. Now, fluence is not a very good parameter to find, to say something solid about the FRBs. So we have moved on to the and total energy emitted from the FRBs, which gives you the intrinsic properties of the FRB source. Now, just plotting the very simple histogram for energy as well. This is also giving you a dip in the histogram, which gives you an idea that the bimodality that we were talking about is true in sense. Now, this dip is around 3 into 10 to the power 41 hours. Now, let us divide the whole population set for FRBs into two categories. One is population 1, which includes low energy FRBs, basically all the FRBs having energy less than 3 into 10 to the power 41 ergs, and greater than that, they'll be called high energy FRBs. Now we have studied different statistical statistical test for the two populations. In figure 1, you can see that the CDF for the two population for the total energy of the FRBs. Now, this separation in the CDF also gives you a hint that they might be coming from the two different kind of data sets. And Anderson-Darling test supports that the two population, that the two samples that we are talking about is coming from the two different populations. They do not belong to the same data set. And then we have run to the fluence as well, then luminosity. All the CDFs are showing that the separation is true in the sense based on the Anderson-Darling test. And the lower plots are just showing the corresponding PDFs for the same parameters. And then dispersion measure. Dispersion measure also shows that the null hypothesis that we have taken, that the two populations are coming from the same data set, is ruled out by the Anderson-Darling test. The second plot is showing the corrected pulse width, which is basically pulse width divided or the redshifted pulse width. Now, these all CDFs ensures that the two populations are completely different. They do not belong to the same wide range of the population. And also, just one thing here, which shows that the brightness temperature, the last figure, spans the whole same parameter space for the two populations. So brightness temperature does not show any wide range variety in the values of the two population FRBs. Now, these are the statistical test table, Anderson-Darling, and also we have done MWW test, which also supports the two population theory. We have also done some correlation test based on the different parameters, estimated parameters, as well as the provided parameters in the catalog. Dispersion measure with total energy, which shows a correlation coefficient of 0.5, and they show that obviously they'll be dependent on each other because total energy gives you I mean, the distance and the total energy are related somehow. So similarly, then luminosity and total energy will also depend on each other, and they show a strong correlation. The main point is that we have calculated or estimated the total energy, and which is theoretically intrinsic parameter, and it depends on various other parameters that are given in the catalog. So it's like we are trying to find dependency so that we can figure out if there is any correlation which can give hint towards the two population kind of thing. And the pink dots represent the population 1, the blue dot represents the population 2, and repeaters are marked differently, right? You can see in the figure number 3, dispersion measure versus luminosity. which shows a distinct pattern in the plot. Like we could find, if we could find, I mean, now we have more data sets, so we are trying to do the same study with the new data set, with the CHIME catalog data set. And you can see that dispersion measure and luminosity also have a Pearson coefficient of 0.42, and they are obviously correlated. Then the brightness, temperature, and luminosity, which shows the Pearson coefficient of 0.44. Now, the next thing is brightness, temperature versus fluence, which is scaled to 1 gigahertz. This shows, this plot is very interesting in a sense that there is a, if one can see, there is a clustering at different centers, like low energy repeaters are falling down, but if you can see, all the repeaters are in the low energy regime, right? Now, there is a clustering at the lower end left corner of the plot and the right upper corner of the plot. So if we are just trying to figure out why this clustering is happening in this particular plot. Now, brightness, temperature versus redshift shows negative correlation with minus 2.7. Then dispersion measure, this is an obvious plot, dispersion measure versus redshift, which shows a very strong correlation of 0.9. And corrected pulse width, which is basically redshifted pulse width versus luminosity. Here also, just similar to the energy versus corrected pulse width plot, the low energy regime, low energy FRBs are falling in the lower end of the plot, lower left end of the plot, and high energy are falling at the upper side. Now, this plot shows a very weak correlation, but if you just see this plot very carefully, we have calculated the Pearson coefficient for two different plots for the all the scatter plots, and this particular plot shows that there is a sign changing in the slope or the Pearson coefficient of the two populations, which might also hint towards the the two set of categories of the FRBs. Then we have done the source count of FRBs. Consider there is a spherical shell of thickness dr. Number of sources in this shell is dn. So dn will directly proportional to dr. And if we just calculate number of FRBs up to a distance r, this will be given by relation number 3. And the peak flux depends, peak flux and luminosity relation is given by equation number 4. Now, using the two equation, we can calculate easily the number of sources up to a distance r, which can be shown differently in a way by equation number 6. Hence, if we just talk about differential source count, the slope should be minus 1.5, right? But what we have find is that okay, so there is a mistake in the caption. It is 118 FRBs because we have excluded Pushchino FRBs, and the remaining and few of them do not have the data set, all the parameters in the catalog, like pulse width is null and other things. So if you can just
3 minutes
see,
remaining.
Okay, I'm just almost done. So you can just easily see that this differential source count, which should have a slope of minus 1.5, does not satisfy. There is a, if one carefully find that there is a two slope, one can easily fit two slopes in the source count, right? Another way of depicting the same plot is that multiply this number, which is y-axis, by fluence to the power minus 1.5 and plot it with fluence. Now, the second plot should have a parallel line to the fluence, but it shows a evolution in the population of FRBs. Now we are trying to figure out if this two slope thing can also give hint towards the two, whether the two population that we are talking about in previous study, population 1 to population 2, have two different kind of slopes, which is under study basically. So the summary says that we find biomodality influence as well as energy histograms, which hints towards the two different kind of FRB populations. Anderson-Darling test and MWW test also supports that the two populations actually exist. Various correlation plots have been shown, which are which are going to be further studied. All the repeaters, all the repeaters are falling into the low energy population. The two population study is very significant to predict whether the two populations are coming from two different kind of progenitor models. If we can correlate that, that will be very interesting to show. Then now the study that we are taking to the CHIME first catalog. We are trying to figure out if CHIME only CHIME FRBs show different behavior than the total of FRBs. So yeah, this was from my side. Thank you.
Thanks, Nidhi. That was a good talk, and it's me clapping on behalf of 79 attendees. We have some time for questions, and please post your questions in the Q&A functionality of Zoom. Okay, we've got one from Vivek, who's asking, do you think that the two subpopulations of FRBs also have different emission mechanisms? If so, why?
Yes, that's what we are trying to figure out. That's just one point in the summary, if you can see. Why so? The main categorizing the population based on the total estimated whether what kind of progenitor. Right now I cannot say anything solid about the progenitor model right now, because one has to figure out not just only the total energy emitted by the source, in fact the other things as well, right? For example, there are many progenitor models roaming around for FRBs. Most popular are like binary neutron star model and other things, right? The point is repeaters fall in the low energy region and low energy FRB population. So why high energy repeaters are not there, etc., are the part of further study. But yes, there is a indication that the two population must be coming from two different kind of sources.
Right, thanks for that. We have some time for a few more questions. Maybe I'll ask a quick one. I think you separated the two populations based on the energy value, right?
Right. Yes.
So what was the motivation behind that? Like, why do you choose that number for separating out the two populations?
Yes, actually, initially we had find out the biomodality influence but fluence is observed thing which do not get altered by the frequency or the wavelength is coming through the intergalactic medium or the Milky Way. We did not wanted any kind of disturbance, which can alter the study. So we move to the total energy emitted by the source. So this gives you hint what is happening at the source, observations. So this is
Okay, thanks for that.
is it okay?
Yeah. Okay, I think we'll move on with the next talk now.
Sure.
So the next, yes. So the next speaker is Mawson Sammons from ICRAR Curtin, and he'll be telling us about the effect of gravitational lensing on fast radio burst source count. Mawson, all yours.
Thank you very much. So yes, I'm a PhD student under the supervision of Kath Trott, Clancy, Mark Walker, and the late and great JP. And so yes, I'd like to kick off with a rather simple example. If we consider we have a population of sources that are all at a constant luminosity, and then we kind of represent these sources visually as randomly distributed about some central observer, then any observation that we take of these sources is going to have some sensitivity or flux threshold, which defines a region in space within which we can observe our sources and outside which they are too faint for us to see. Now, gravitational lensing can apply a magnification that boosts the observable flux so that we might see sources from beyond this kind of physical boundary. This is going to change the shape of our luminosity function, as we'll get contributions from sources with apparently higher luminosity than we would have intrinsically expected. Now, understanding this kind of effect is important because we observe this lensed distribution rather than the intrinsic, and each of the components that go into it can tell us something about the properties that go into it. Namely, the intrinsic distribution of FRBs is quite important, as we just saw, for kind of finding out things about the intrinsic population and emission mechanisms, whereas the magnification PDF that gets convolved with this intrinsic distribution to give us what we observe depends upon the universe's mass distribution. And so if we want to find out things about the properties of dark matter and whatnot, this property can be quite helpful. So this gravitational lensing PDF is effectively the probability that our source FRB here is going to be magnified by some value mu. Now, if we visually represent this as red ellipse cross sections to lensing at a magnification greater than mu, and have our FRB source here, which currently falls short of our observation, if our source is then seen from behind one of these cross sections, its flux gets boosted and we'll be able to observe it. So clearly the probability that we're going to lens this source depends upon these cross sections greatly. In previous works, what has been done is these cross sections have been mapped from their local lens plane into the source plane, and the fraction of the area in the source plane that they occupy gives us the probability that our source will be magnified by some value. Now, the mapping between the local lens plane and the source plane is a little bit more complicated than a simple projection, but nonetheless, the essence of what's going on is captured in this kind of graphic. And this model is quite good for the scenario we've got here. We have a low number of lenses. There's no overlap between their projected cross sections on the source plane, and they're quite far separated from one another. However, if we start to remove our source FRB and place it more and more distantly in the universe, we expect more and more lenses to come along the line of sight, and we might end up in a regime that looks a little bit more like this. Now, as our source passes by more than one of these cross sections, we go through what is called multiple lensing, which is a highly nonlinear process that's really only suitable to treatment via a numerical simulation. Now, numerical simulations are quite often computationally limited. So in this project, we wanted to see how far we could get with an analytical calculation alone. So to get ourselves out of this situation and back into a realm that can be treated analytically, what we can do is recognize that as we place our source further and further away in the universe, we require a higher and higher magnification for it to remain observable. As we increase the magnification, the cross-section of our lenses gets reduced drastically. And so we can happily remain in a kind of low optical depth regime where there isn't too much overlap between our cross-sections. However, no amount of reducing the cross-section size is going to change the separation between our lensing objects. Now, if we want to treat a rather large number density of lenses, we're going to need to kind of treat how these objects interact with each other gravitationally, as they'll affect the shape of each other's cross sections. This can be known as shear, whereas convergence or Ricci focusing gives us the traditional magnification of a source image. A shear can result in a distortion or a stretching of that image in one direction. As we see here in the famous Cheshire Cat lens, these external galaxies have been stretched quite severely around the outside. Now, treating this shear has been done previously. In 1984, Nityananda and Ostrika found that for a two-dimensional screen, we can place an arbitrary distribution of point lenses that all contribute to the shear of the ray in the middle, but we can find an analytical and completely nonlinear solution to this problem. Now, this is quite good if we wanted to treat the lensing for a distribution of, say, stars in a halo, as a halo is quite well approximated by a thin screen. However, if we wanted to take on something a little bit more complex, such as an extended three-dimensional distribution of, say, primordial black holes in the intergalactic medium, we're going to need to take this treatment a step further. This has also been done previously by taking a host of these kind of lens planes and stacking them back to back, then processing our ray in a simulation sense through this stacking of screens. Now, if we wanted to avoid the simulations, like we said earlier, we can make some simple approximations to take the discrete stacking of lens planes here to the continuum limit and give us a PDF that includes the shear for an extended three-dimensional distribution of point lenses. Now, this approximation that we make here removes the fully nonlinear results of this calculation. However, we still get out an approximation of the shear, at least to the first order. Now, as we said before, the low magnification regime is where our model is going to start to run into some trouble. So clearly we can't use all of this treatment. However, what we can do to have our model remain functional is we can crop our model at some suitably high magnification where it's still usable, and substitute the remainder of it for a delta function that is constrained by these integral constraints for our probability distribution function, namely that it has to be normalized to a value of 1, and the expectation value of our magnification has to match the area average magnification of the universe at that redshift. So now what remains is to determine this area average value. And to do so, we kind of need to understand how cosmological distances play into the mix. So traditionally, if we assume a homogeneous universe where matter is smoothed out everywhere, as is the standard, we get a very intuitive picture of the angular diameter distance given by these magenta lines, where an observer sees the source object here in the blue. And the density of matter within this beam is the same as the outside, so we get, yes, these very straight kind of unperturbed lines. However, as we start to remove matter from the inside of this beam and place it outside, the density on the outside becomes greater, and our lines are likely to get deflected away from the observer off to this denser part of the universe. This means that what the observer is going to see is these black deflected lines, and if we trace tangent from the observer's point of view, their angular size of the source is going to be greatly reduced with respect to what we would expect for the source's physical size. Now, the angular diameter distance is given as the physical size of the source over its perceived angular size. And so with a much reduced angular size, it appears as though our source is at an apparently larger angular diameter distance. In a slightly more intuitive picture, if we set up a kind of a toy universe here, where this eta fraction describes the portion of our matter in our universe that is homogeneously distributed. Here we have the standard assumption picture, where we have our very easily understandable angular diameter distance with the density inside the cone that's identical to outside. However, if we start to take some matter from this pool of homogeneity and congeal it into compact objects, we end up with a separate distance known as the empty beam distance. This empty beam distance avoids the clumps, and so we'll experience a density of matter within its beam that's lower than the outside, which extends its angular diameter distance apparently. If we continue to reduce the fraction of smooth matter we have all the way to 0, this is going to extend even further. And so what is the ultimate difference between this empty beam distance and the homogeneous angular diameter distance that we traditionally think of? Well, it turns out that if we evaluate these two cases in the extreme, so our clumpy universe is the orange and our completely smooth universe is the blue, in the nearby universe, there's not all too much difference, but at higher redshifts, we start to notice there is a large discrepancy between the two. This is kind of important because the The ratio of these distances squared is what gives us our area average magnification in the universe. And so at a high redshift, we might expect this value to be quite large. Now, all that remains now is to kind of investigate how do we determine this eta value and what is it for our universe? Well, it's a little bit complex because it actually depends on the scale of the observation that we're taking. This can be understood as if we consider this purple magenta line here, for a rather large angular size of source, these small scale compact objects, which are small scale inhomogeneities, are going to be averaged over by this observation because they're quite granular with respect to the volume of this beam. This means that the density of the cone inside is going to be the same as outside, and we get back the very standard picture of our angular diameter distance. However, if we have quite a compact object, we might expect that the density will fluctuate quite highly, and so our angular diameter distance might shift with position. Now, currently, observations tell us, such as the dispersion in the MZ relation for supernova, that the universe is approximately smooth with an eta value of 1. However, a canonical supernova has a co-moving volume in its beam of about 1,000 parsecs cubed, which is quite a bit larger than the volume to a canonical FRB, which is about 1 astronomical unit cubed. And so we can see that we're going to probe vastly different mass scales here. What are these mass scales? Well, if we take these co-moving volumes that's subtended by these canonical sources, and we multiply it by the average density in our universe, we get out a mass, a characteristic mass for this beam. If our inhomogeneities are larger than this characteristic mass, we expect less than 1 per beam, and so the universe will appear inhomogeneous. From the constraints from supernova, we can say that we don't really expect any heavier inhomogeneities than about 10 to the negative 5 solar masses floating out in the intergalactic medium. But below this, it's anyone's game. For FRBs, they probe a much greater range of inhomogeneities than supernova. And so we might be able to say something interesting. Namely, this shaded black region here is the currently unconstrained region of primordial black holes in the literature. And so FRBs might provide us with a way to explore an entirely unconstrained region of dark matter parameter space. Now that we have a way to treat these eta values and so we can calculate our area average magnification, we can complete our model and actually now get out some source counts. So in this plot here, we've got on the y-axis differential source counts for a lensed population normalized by the differential source counts of an unlensed population. And on the y-axis, we have the flux of our observed source normalized by the flux that it would have if it were at a redshift of 1 in a completely smooth universe. The two plots here are for a nearly smooth universe with a smooth matter fraction of 0.99, and for a universe that has 100% of its matter in compact objects that form our lenses. Now we can see, as expected, that our nearly smooth universe effectively matches the unlensed case at a 1-to-1 ratio. However, we see the eta equals 0 case has a rather different shape. Now, for all the values left of about log s
3
of
minutes
1,
left, Mawson, 3 minutes.
Oh, thank you very much. For all the values left of about log s of 1, we can kind of ignore the shape of this because this is somewhat an artifact of the process. In this calculation, we only placed source objects out to about a redshift of 10, which means that as the magnification goes up to infinity, we can no longer continue to lens source objects into our account. However, in the nearby universe, we see that even in this extreme case of 100% of our matter being in lensing objects, we still only lens it about a few percent. So this means that lensing might not be all too important for what we're considering. However, we can temper this kind of result with the knowledge that, as we explained earlier, this is for a very simplistic delta function distribution, and we're only calculating bolometric quantities in this kind of very preliminary work. So what we'd like to do now is extend this to a more realistic picture with a non-delta function luminosity for our sources, some spectral dependence, and we'd like to begin working with observables that are much more FRB-like, such as fluence and energy as opposed to flux and luminosity. And once we've done this, we can start getting out a picture of the lensing that is a little bit more realistic and see if it has more of an influence than it did in the simple delta function case. Some of this work is being baked into publications at the moment. There's one submitted and one to follow. So thank you very much. A little bit under time, but leaves more time for questions if there are any. Cheers.
Thanks, Mawson. We have one question from Hassan, who is asking, is there any difference or similarities for gravitational lensing between FRB and pulsar?
Yeah, so obviously these are both kind of compact objects. The difference is that they probe a rather different volume. Obviously our FRBs are at quite a far removed distance, whereas pulsars are quite close, but they still get lensed in just the same way by, say, a compact object along the line of sight. They just probe rather different kind of densities, I guess.
Okay, we have time for some more questions. We have one question from Ryan, who's asking, can the formalism be applied to cold dark matter with substructure?
Yeah, I mean, so you can take it a number of different ways. So cold dark matter normally has some kind of hierarchical clustering. So normally that's what goes on in a lot of the models there. Currently in this case, for calculations like this one, I've assumed a homogeneous distribution, or sorry, like a uniform distribution of lensing objects. So that'll be work for the future, will be to kind of maybe introduce some clustering into the mix, but you can certainly do these calculations for cold dark matter objects. If you wanted to take it to a particle limit, you end up with less cold dark matter objects, in the sense that you end up with less compact objects. So this treatment would have to be slightly different, but you can still end up with clusters of mass that can form your ostensible lensing objects in that case. So yeah, there's no reason why this can't be extended to that.
Any further questions? Well, if there are no follow-up questions, thanks, Mawson, again. And
yeah, no worries.
We'll move on to our next speaker, who's Pragya Chawla from McGill University. And she's going to tell us all about FRB CHIME catalog and interpreting FRB dispersion measures and scattering. All yours, Pragya.
Thanks, Shivani. I'll just share my screen. Okay. Hello, everyone. I'm Pragya. I am working with the CHIME FRB collaboration. And today I'll be talking about the first CHIME FRB catalog that was recently released, but I will be specifically focusing on the interpretation of the dispersion measures and the scattering timescales of the bursts in the catalog. So briefly, CHIME is the Canadian Hydrogen Intensity Mapping Experiment. It is a transit telescope located in British Columbia in Canada, and it comprises of 4 cylinders, each 100 meters in length and 20 meters in diameter. Each of these cylinders is fitted with 256 dual polarization antennas, which are sensitive in the frequency range of 400 to 800 megahertz. The field of view of each of these antennas is about 250 degrees, extending 120 degrees in the north-south direction and ranging from 1.3 to 2.5 degrees in the east-west direction. So the inputs from all of these 1024 antennas are combined with appropriate phase delays to form 1024 beams on sky. The data for all of these beams is searched in real time with a frequency resolution of 24 kilohertz and a time resolution of about 1 millisecond. Since CHIME is a transit telescope and only observes directly overhead, all of these beams are located in a small strip of sky that is located directly overhead. The map on the right shows the scale of these beams as compared to the sky in galactic coordinates. However, CHIME operates 24/7, and that means that over the course of the day, CHIME can end up observing the entire sky that is visible from the northern hemisphere. This large exposure results in a relatively high detection rate for CHIME, averaging at about 3 FRBs per day. The large detection rate has greatly changed the FRB detection landscape. So before CHIME started operating, that is in June 2018, there were about 60 FRBs known. The observing frequencies of these FRBs are shown here in the histogram on this plot. Within a year of operations, CHIME has detected over 500 bursts, bringing the total number of detections to about 600. the bursts that were detected in the first year of operations are included in the first CHIME FRB catalog. These bursts include about 474 one-off FRBs and 61 bursts from 18 repeating sources. The dynamic spectra for 25 of these bursts is shown on the right, with frequency on the y-axis and time on the x-axis. The dispersive delay has been corrected for in all of these bursts. Some of these bursts show complex structures, showing multiple peaks that drift downward in frequency, while others show exponential scattering tails, which are caused by multipath propagation in the inhomogeneous intervening medium. As part of the catalog, we measure the properties of all of these bursts. These properties include fluence, dispersion measure, width, scattering, and the spectral parameters. We also provide localization regions, which are derived based on the detection signal to noise in adjacent beams. And these localization regions are of the order of about 15 arc minutes. While the first CHIME FRB catalog only included bursts that were detected up to July 2019, the CHIME FRB system now has a real-time alert service through VO events. We have been testing this alert service, working with some groups, and have successfully triggered low latency follow-up of several FRBs. This service will become public soon, at which point subscriptions will be available to anyone. So all the FRBs going forward will be shared with the community as soon as they are detected. So back to the catalog. The sky distribution of these 535 bursts is shown in the plot on the top right. In blue are the bursts which are not found to be repeating, while in orange are the repeating sources that are detected with our system. So we first test whether this distribution is isotropic or not. This is an analysis done by Josephi et al. And this was motivated by the suggestion from some park surveys that there is a reduced rate of FRBs at low galactic latitudes. So when we plot the cumulative distribution function of the detections of FRBs that we see with CHIME, which is shown in the solid black line here, we find that it closely follows the exposure, which is shown by the dashed black line, indicating that there is no evidence for reduced rate of FRBs at low galactic latitudes. We also cross-correlate the sky positions of all of these FRBs with different galaxy catalogs, and find that these FRBs cross-correlate with galaxies in the redshift range of 0.3 to 0.5. More details about this analysis will be presented in a talk in the Cosmological Probe session by Masood Rafi Ravandi. So we also analyze the morphology of all of these bursts, and we find that similar to the first repeating FRB source, FRB 121102, that repeaters exhibit complex morphology. An example of such a burst is shown on the right. So repeaters have these multiple peaks, and we also observe downward drifting subbursts. So subbursts, the frequency for which decreases as time progresses. When we compare the repeaters versus non-repeaters, we find that most of the distributions for most of their properties are indistinguishable from each other, so are consistent when we use the Kolmogorov-Smirnov and the Anderson-Darling tests. However, for two properties, we find that the repeaters and non-repeaters have different distributions. So the plots here show the one-off bursts in green and the repeaters in orange. As you can see, repeater bursts tend to have larger widths as compared to the one-off sources, and they have narrower bandwidth. So repeater bursts seem to occupy anywhere between 50 megahertz to 400 megahertz of our band, while most one-off bursts have a bandwidth that is equal to the full observing bandwidth for CHIME, so about 400 megahertz. So once we have the properties of all of these bursts, we can also plot their DM distribution. This plot is shown here in the left panel. However, this is just the observed distribution of FRB DMs with CHIME and has to be corrected for the selection function. We determine this selection function by injecting signals into the real-time detection pipeline to determine the probability with which a burst will be detected. This selection function is shown here in the top panel. As you can see, we have high sensitivity to bursts with DMs ranging from anywhere between 200 to about to about 1,000 or 2,000 units. However, we have low sensitivity to bursts with relatively low DMs, as well as bursts with DMs greater than 2,000 units. So once we have the selection function, we can correct the observed distribution by dividing it by the selection function. So on the right, we have the intrinsic DM distribution of the FRB population that is shown here in blue. And we can also repeat this process for other properties. So for example, the scattering time distribution. The observed distribution again is shown here in the left panel in blue. And the selection function that we determine using our injection pipeline is shown at the top. The selection function for the scattering times is a bit different in the sense that we have reduced sensitivity to bursts with really high scattering times. And we are almost missing bursts that have scattering time scales greater than few tens of milliseconds at 600 megahertz, so the center of our bandwidth. So once we divide out this observed distribution by the selection function, we get the intrinsic distribution for the FRB population, which is shown on the right. And as you can see, we find evidence for a large population of events that are highly scattered, so which have scattering times greater than 10 milliseconds. These selection corrected distributions can be used to determine the FRB rate as well as the fluence distribution index, which will be discussed in a talk by Kaitlyn Shin in this session. So now we can analyze why we are seeing this large population of events that have scattering times greater than 10 milliseconds. To do this, we use a population synthesis framework. This framework simulates the intrinsic properties of FRBs, such as their energies and redshifts. And then we also simulate the scattering and dispersion measure contributions of the different intervening media that FRB signals propagate through. These intervening media range from the Milky Way ISM to any intervening galaxies that the line of sight to the FRB encounters, the intergalactic medium, the ISM of the host galaxy, and the local environment. We adopt different prescriptions for the electron density in each of these media, which allows us to evaluate the dispersion measure of the simulated bursts. We also adopt prescriptions for the level of turbulence in each of these media, so the fluctuation parameter here, which allows us to evaluate the total scattering measure for each of these bursts. So once we have these prescriptions, we can get a distribution of scattering time scales and dispersion measures, and then compare it with the selection corrected catalog and test different population models using this comparison. So just to give a brief overview of the models that we are simulating. So starting with the Milky Way ISM, we use the NE 2001 model to simulate the DM and the scattering contribution for the Milky Way. The dispersion measure of the intergalactic medium is estimated using the Macquart relation. As of now, I'm skipping intervening galaxies and the local environment, but I'll talk about those in a bit. As for the host galaxy ISM, we assume FRBs to be located in 3 different types of galaxies: spiral galaxies, elliptical galaxies, and dwarf galaxies. The electron density distributions that we are using for each of these galaxies have been taken from these references. I won't be going over all of these distributions in detail in the talk, but feel free to ask me about these in the questions. As for spiral galaxies, we know that they have a high free electron density. Therefore, if FRBs have different spatial distributions within a spiral galaxy, then that would lead to different DM and scattering distributions. That's why we test 3 different spatial distributions of FRBs within spiral galaxies. These spatial distributions resemble the pulsar and the magnetar populations in the Milky Way. And the third distribution resembles the spatial distribution of short GRB populations. So the first 2 populations here, pulsars and magnetars, are preferentially distributed along the spiral arms, while the short GRB populations are expected to be offset from the galactic centers.
So the 3 minutes left.
Yeah, thank you. The resulting DM distributions for these models are shown here. And as you can see, dwarf and elliptical galaxies have lower DMs as compared to the spiral models. The scattering time distributions for the same models are shown in this plot. And for dwarf and elliptical galaxies, we assume the turbulence to be the same as that for the thick disk of the Milky Way. So once we have the simulated models, we can combine the scattering contributions of the Milky Way, the intergalactic medium, and the host galaxy, and then compare the resulting scattering time distributions with the catalog. So in order to do this, we vary the power law index of the simulated energy distribution to first match the DM distribution with the selection corrected catalog. Once we have the DM distributions matched, we can compare the simulated scattering times with the catalog. When we do this comparison, we find that if we only include the scattering from the ISM of the host galaxy, then we cannot reproduce the observed distributions. So the plot here on the right in blue shows the selection corrected catalog, and all of the other colors show the different models that we are simulating. As you can see, none of these models can match the large population of highly scattered events. So now we need to invoke additional sources of scattering. We start with adding high electron density local environments to all of the simulated FRBs. These environments are modeled based on the observed DMs and scattering for pulsars from the NE 2001 model. And the simulated local DMs range from about 10 to 300 parsec per centimeter cube. So the plots that I'm showing here show something similar to what's shown here, except that this is the cumulative distribution function. In blue is the catalog. And in green here shows a distribution of FRBs with no contribution from the local environment. Once we add the contribution from the local environment, we find that the scattering distribution seems to match a bit better, but is still inconsistent with the catalog. So we go further and increase the minimum local DM to 50 parsec per centimeter cube. So in increasing the DM contribution of the local environment, we end up increasing the scattering contribution as well. However, we now find that this results in a lack of low DM FRBs, although the scattering distribution matches much better as compared to the other two alternatives that we tried. This suggests that FRBs inhabit environments with higher scattering per unit DM than those observed for galactic pulsars. We also try other scattering models. So we include scattering in the circumgalactic media of intervening galaxies. This could be caused by cool ionized clumps in the CGM, as was proposed by Vedantam and Finney. We find that after adding this source of scattering, this relaxes the requirement of local environments having extreme properties. As you can see in the two plots here, where the catalog distribution in blue is compared with the simulated distribution, we can explain some fraction of this large population of the highly scattered events. However, this distribution is still marginally consistent, and there are a lot of bursts which cannot be explained well by this model. So the main conclusion that is emerging from this analysis is that at least some fraction of the FRB population needs to inhabit environments with extreme scattering properties to be able to explain this large population that we are seeing with CHIME. I leave you with a summary, and I'm happy to take any questions at this point.
Thanks, Pragya. We have a question from Ray, who's asking for the elliptical galaxy modeling. As we know, Zhu and Han 2015 merely used the part of this thick disk for NE 2001 to model the ellipticals. However, the elliptical looks spheroidal observationally. The electron density model should be built using spheroidal gas functions rather than a disk. How do you address this?
Yes, so we had tried a bunch of different models. There are some X-ray observations that give an idea of what the electron density distribution for elliptical galaxies is as a function of radius. And we find that even if we try those models, the DM distributions that we end up with are pretty much the same as the distributions that we see by just assuming the Milky Way thick disk. So in order to be consistent with the literature, for now, we are just assuming the Milky Way thick disk to be an approximation for the elliptical galaxy, but we have tested a couple of different models, but none of those seem to drastically change the DM distributions that we get in these simulations.
Thanks for that. We have another question from Keith, who's saying, is CHIME searching for narrowband FRBs in a different way to broadband FRBs?
So for now, no. So when we end up searching for FRBs, we search for them using 3 different spectral indices. So searching for a flat spectral index, which means summing the signal in all of our bandwidth, And then we also try two other options. So spectral indices of -3 or +3, so giving different weighting to different regions of our bandwidth. So in some way, like those two different spectral indices do favor narrowband bursts. Say you had a burst that was very bright in one part of the band, you would expect to detect it with a higher signal to noise in the different spectral index searches. But no, we are not specifically doing searches where we split the CHIME band into different subbands and search for narrowband bursts. So we have some sensitivity to narrowband bursts if they are at the edges of the band, but we're not doing specific searches.
Thanks for that. We have a question from Ryan, who's asking, have you considered the ISM scattering increasing in strength with redshift? High Z galaxies have high levels of turbulence.
No, so that is not something that we consider in these simulations. Here, we are just assuming all spiral galaxies to be like the Milky Way. The only thing that we are so the only parameter that we are distinguishing between different spiral galaxies is that we are varying their radius based on some mass distribution, but we're not considering any redshift dependence to the scattering.
We have another question from Paz, who's asking, are the models for the different populations assuming Milky Way-like DMs? And we expect the local DM to depend on galaxy mass and redshift.
Yeah, yes, so we do consider different galaxy masses. We take, so for the spiral galaxies, initially we assume a Milky Way-like model, and then we assign a different radius to each of these spiral galaxies and scale the electron density distribution by that radius. Yeah, so we end up considering the galaxy masses that way. We don't consider the redshift dependence. But that is something that can be considered, say, in the future studies. For now, we were just intending to sort of test like an initial distribution of galaxies. Although I don't think that would change the result significantly, since what we are seeing is that there is such a drastic difference between our simulated models and the population that we're observing, that even if the distribution function changes slightly, our results shouldn't change.
I'll take another quick question. Pavan is asking, did you try local scattering model where the Kolmogorov initial range of eddies is different, and or where the local size of the scattering screen is less than 50 parsec?
No, so we did not try those models. We did add like different scattering timescales from the local environment. So if the observed DMs and scattering that we see for pulsars, if their scattering timescales are valid for models where the screen size is about 50 parsec, then those effects would be included. But we did not explicitly consider any scattering index different from -4 in our analysis.
Thanks, Pragya. I guess we'll take another questions offline, and I'll post them on Slack. And thanks again.
Thank you.
And now I'm going to introduce, so there is a swap of talks now, and we are going to, first Kaitlyn Shin is going to talk to us about FRB population distributions from the CHIME FRB catalog. All yours, Kaitlyn.
Awesome, thank you. Okay. So hi, I'm Kaitlyn, and I'm a graduate student at MIT working with Professor Kiyoshi Masui and the CHIME FRB collaboration. And today I'm going to be talking about results on FRB population distributions from the first CHIME FRB catalog. So since I'm directly following another CHIME FRB catalog 1 talk, I'll keep this background extraordinarily brief. So as a quick refresher, the first CHIME FRB catalog sample has detected 535 FRBs in roughly the span of a calendar year, and the sample includes 61 bursts from 18 repeating sources. And for each of these bursts, we've measured associated properties such as fluence, DM, scattering timescale, and intrinsic pulse width. So now there are certain questions about distributions of properties that are easy to ask, but hard to answer. For example, how are the observed brightnesses of FRBs distributed? And also, what is the overall sky rate of FRBs? And the reason why these questions are so hard to answer is because we can't take our observed measurements at face value. We need to account for selection effects if we want to properly answer these questions. And this is something that the first CHIME FRB catalog sample has done. And so kind of as I hinted before, the observable properties that we're studying are the fluence, the dispersion measure, the scattering timescale, and the intrinsic pulse width. And the key to kind of studying these properties while accounting for the selection effects is the injection system. And so for more details on the injection system, definitely check out the poster and/or lightning talk by Marcus Merrifield. So what we do with this injection system is we inject events into our real-time detection pipeline with a wide range of parameter values so that we can calibrate our observed selection function or selection effects as a function of all these FRB properties that we are considering. And so in order for our injection sample and our observed catalog sample to be comparable, we have to cut any bursts from the catalog 1 sample that we think has a selection effect that's not captured by the injection system. So we can take signal to noise as an example. In the CHIME FRB catalog, all these real bursts basically undergo double human verification, where we look at these bursts and we're like, is this real or is this just noise? So it's entirely plausible that for lower signal to noise bursts, humans might accidentally miss some of these bursts, misclassify them as noise or something. You know, we're only human. And obviously this is a problem that the injection system just doesn't run into. And so how do we quantify this human incompleteness bias? We just can't. And so one of the cuts that we make to the catalog 1 sample is we cut all events below a signal to noise of 12 because we say it's only a signal to noise of 12 or higher that we humans are complete and can catch all the bursts the same way the injection system catches all the bursts. So now we can combine both the injection sample and the observed catalog sample to fit a fiducial model that reasonably describes the FRB property distributions. And for this first catalog sample, we're making a key assumption, which is we are assuming that the properties of these FRB properties that we measure are intrinsically uncorrelated. And this allows us to assume that the intrinsic joint distribution of all of these properties neatly factorizes into intrinsic individual distributions. And of course, in principle, all these intrinsic FRB properties should be modeled and fit simultaneously if we want to be fully self-consistent, but that's something that we're going to defer to future work. Now, what this model doesn't assume is that the selection effects factorize, or in other words, the simplified fiducial model, this enables us to deal with correlated selection effects of the observed properties. So what do I mean by a correlated selection effect? An example, we can take DM smearing as an example. So for a lower DM burst, that might be a narrow burst. If it like within a frequency channel, it might not have much of a temporal smearing response. But for a higher DM burst, because it travels so fast from high to low, top to bottom frequencies, it could induce a temporal smearing response within a channel, which means when we average over that frequency channel, the observed burst might appear to be wider than it actually is, but then when we subtract out the smearing effects, we might accidentally miss the high DM narrow burst. But if this high DM burst is intrinsically wide or has an intrinsically large pulse width, the observed pulse width is no longer dominated by the temporal smearing, and so we're less likely to miss this high DM burst. And so this is kind of what I mean when I say there's a correlated selection effect, and in this case, it's between the DM and the intrinsic pulse width. And so from the injections in the fiducial model, we can calculate selection functions, and we do calculate selection functions for the DM, the scattering timescale, and width distributions. And something that I really want to reemphasize is that the selection function of one property, such as DM, depends on how the other properties are distributed. And that's why we have to fit this fiducial model so that we're able to kind of deal with these properties together. So I'll start with the results for the scattering distribution. This is scaled to 600 megahertz. And so what we see in the main left-hand panel is the raw catalog distribution before compensating for selection effects. And then on the right is the distribution after we compensate for selection effects. And the fiducial model is overlaid on top of the distribution as well. In this case, the fiducial model for each of scattering, DM, and width are assumed to be a simple log normal distribution. And in the upper left-hand panel, we can see the selection function is plotted. And so as Pragya had mentioned in her talk just earlier, we see a severe selection bias against events with a high scattering timescale above 10 milliseconds. And this is reflected in the shaded region of the histograms. And if we look in the left-hand panel, for example, the raw catalog distribution, we see just a handful of highly scattered events, say the last two bars of this histogram. But if we look at the right-hand side plot, we see that in this area, the distribution is poorly constrained. And this is, so basically what our injections is telling us is that in order for the CHIME telescope to have even detected this handful of highly scattered bursts, there must have been an even larger population of undetected bursts that have high scattering. And the uncertainty is large, of course, but it does seem like the bursts are there. And so to explain this amount of scattering, it does suggest that these FRBs must inhabit environments with strong scattering properties. And of course, I'm sure you all recall the talk that Pragya Chawla gave 20 minutes ago for more on this interpretation. So now I'm showing the results for the DM distribution. And if we look at the selection function in the upper left panel, it seems that while we are biased both against lower DM and high DM events, we seem to have larger biases against low DM events from, say, detrending and flagging effects, rather than against high DM events, which might occur because of the DM smearing example that I gave earlier. And so now here I'm showing the results for the intrinsic pulse width distribution. And once again, if we look at the selection function, it appears that we select against wide events. Yet when we look at the main histogram distributions of the panel, we see that unlike the scattering distribution, there doesn't seem to be much evidence for a large unobserved population of bursts with intrinsically large pulse widths. So now I'm going to talk about the fluence distribution of FRBs, including a measurement of the absolute rate on the sky. So we can model the cumulative fluence distribution as a power law parameterized by this power law index alpha. And in the Euclidean expectation, the alpha index is -3/2. And the measured power law index values for this FRB brightness distribution distributions that we see in literature are pretty discrepant, even after taking into account error bars, and I've listed a few examples there. So I guess, where does CHIME FRB come in? So in order to estimate both alpha and the all-sky rate with our first catalog sample, what we do is we fit the joint distribution of fluence and DM. And there's actually a little subtlety here. We actually use signal to noise as our observable proxy for fluence. And that's because we can forward model our signal to noise measurement with the injections, but that's something that's hard to do with fluence measurements because all that happens in an offline pipeline. So anyway, we then draw MC samples from this posterior distribution, and we find an alpha value of -1.4 plus or minus about 0.1, which is consistent with this Euclidean expectation, as well as an all-sky rate of about 800 FRBs per sky per day. And this is above a fluence pivot of 5 Jansky milliseconds, scattering timescale of 600 megahertz, and above a DM unit of above a DM value of 100 units. And so this Euclidean expectation only really holds if we include sources at all the distances, but we would expect there to be distance scale induced correlations between fluence and DM. And so we can take this kind of generic toy model illustration that I've shown here on the left, where we have this energy distribution. It's concave down so that the total energy doesn't diverge. And so for more near sources or lower DM sources, we would expect to preferentially sample the lower energy, shallower part of the luminosity function. And likewise, for further away higher DM events, we would expect to preferentially sample the higher energy, steeper part of the luminosity function. And so when we split our sample into a low DM sample and a high DM sample and redo the analysis, where low DM and high DM, the split is at 500 DM units, which is close to the median DM value of our sample. We see on the right hand, so if the left is a toy model, the right is actual data. And we see on this right hand plot significantly different values of alpha between the low DM and the high DM samples. And so as expected, the low DM sample has a shallower alpha value of about -0.9, and the higher DM sample has a steeper alpha value at about -1.8. So
Kaitlyn, three minutes left.
Thank you. And so it's clear that this joint distribution of dispersion measure and fluence holds a lot of information. And we can fit a more physical model to the intrinsic distribution, similar to what Clancy James presented earlier this session, to get information about the underlying FRB luminosity distribution as well. And preliminary work is already underway for this. And so kind of to wrap up, with this first CHIME FRB catalog, we've detected 535 new FRBs. And not only that, we've also characterized the selection biases, which is useful for properly measuring the intrinsic population property distributions. We've also found evidence for a large population of highly scattered FRBs, which is strongly suggestive of some FRBs having their origins in highly scattered environments, such as, dense turbulent ones. And we've also measured an alpha value consistent with Euclidean expectations, as well as seeing evidence for distance evolution of the brightness function. And I've also finished a little bit under time, but I'm happy to take any questions.
Thanks for the great talk, Kaitlyn. Time for some questions. I can see one question from Ron, who's asking, how well can you distinguish between exponential scattering tails and broad intrinsic pulse width?
There's definitely a correlation there. And I guess I don't have a quantitative answer for how well we can distinguish between them. We do, for some events that are more difficult to measure, we do just have upper limit values as opposed to like actual precise measurements. And that's something that we also take into account for this analysis.
We have another question from Vivek, who's asking, for FRBs which have more than one components, what values of intrinsic width do you quote? That is quadrature sum of widths of individual components?
So for bursts that have, for complex bursts, I believe what we do is we use the associated boxcar width for that particular overall burst. I'm not sure if that answers the question well, but I'm pretty sure that's how we handle that.
Okay, we have time for a few more questions. Last chance before I move. Okay, so since there are no follow-up questions, thanks a lot, Kaitlyn. And yeah, we'll move on to our next speaker, who is Mohit Bhardwaj. And he's from McGill University, a PhD student, and he's gonna tell us about discovery of local universe FRBs by the CHIME FRB collaboration. All yours, Mohit.
Thank you, Shivani. Can you see my screen?
Yes, I can.
Awesome. So hello, everyone. My name is Mohit Bhardwaj, and I'm a PhD candidate at McGill University, and also a member of CHIME FRB collaboration. Today, I will be telling you about two local universe FRBs that were discovered and localized by the CHIME FRB collaboration. And because Pragya and Kaitlyn have already provided an excellent overview of the CHIME FRB project, I'll get right into discussing low DM FRBs. Now, I think when I talk about low DM FRB, the first question you guys might ask, why low DM FRBs are so special? Why to study them specifically? Now, the most obvious answer is, which is, I think, sort of conspicuous, is that these sources are quite easy to study in terms of their local environment, mostly because of the sensitivity constraints of our telescopes. And also, if you want to follow up, for example, the prompt or afterglow emission that are proposed by different models for FRBs, these are your best candidates. And more important to my talk, low DM FRBs, it is specifically possible that even with minute localization, we can actually say something about their host, and which is sort of described in the plot that is shown on the right. So on the x-axis, we have excess or extragalactic dispersion measure. On the y-axis is the effective localization radius, and these two plots shows the chance coincidence probability of finding an FRB 1102 like host, which you know that is the faintest FRB host discovered too late. And for excess DM of around 50 to 100, it is possible to actually say with some statistical confidence that this specific galaxy is the host of the FRB. So that's one important reason why I am interested in low DM FRBs. There are other applications as well. For example, we can constrain the luminosity function of FRBs very well. We can test different progenitor models using by studying even the fainter and substructures of these nearby FRBs, which will be discussed in the conference later on, definitely. And another important application of low DM FRBs is that you can actually constrain Milky Way halo contribution, which is poorly constrained by all the available constraints we have, for example, from the emission line in UV and X-rays. Now, so let me first dive straight into the paper that we have published recently. It's on the detection or the discovery of a very nearby FRB that is localized at the outskirts of M81. Now, this FRB was first discovered back on January 20th, 2020. That's why its TNS name is 2020-0120E, because it's the fifth FRB discovered or at least reported to the TNS on that day. So using the baseband data, we localized this FRB to a sky area of around 14 arc minutes. Now, by just looking at its low DM and RM excess values, one can say that this FRB is likely to be in the nearby universe, or for specifically in this case, we estimate the maximum redshift to be around 0.03. And its local environment is not as dense and highly magnetized as we have seen in the case of FRB 1102. Now here I showed the waterfall plots for the three bursts that we have reported in the paper. Now for two of them, we actually saved the baseband data. So one interesting observation that you can see specifically in this waterfall plot of the baseband, waterfall plot of this specific FRB is the downward drifting substructure, which is thus far exclusively seen in the frequency versus time waterfall plots of repeating FRBs. So that actually makes an interesting case of maybe this FRB, at that time, maybe this FRB is an extragalactic source. Now, here comes the catch. Low DM FRB, though they are very promising sources, it is very difficult to assert conclusively that that specific FRB is indeed extragalactic. And it is mostly because of the high uncertainty in the Milky Way and its halo DM contribution. Though I should acknowledge that the Milky Way DM models do take into account some actual observations, but the available Milky halo DM models, they are poorly constrained, I can say, due to the paucity of useful observations. Application of the FRB shown in the title of the plot changes if we assume different DM contribution of the Milky Way host and halo. So, and that's why it is very important to first make sure that these are extragalactic. So in this case, we looked at both galactic as well as extragalactic possibility of this FRB origin, and found extragalactic origin to be more promising, mainly because of the absence of any plausible galactic counterpart. And interestingly, we found M81, an early type spiral galaxy at the distance of 3.6 megaparsec, close to the FRB localization region, that is not just satisfy the observed DM excess of this FRB, but also the chance coincidence of finding this M81-like galaxy purely by chance that close to the localization of this FRB is very low, less than 1%. So that actually makes this M81 the promising host of this FRB. Now, the most intriguing twist in the story of this FRB origin came when the precise EVN collaboration actually localized this FRB to an M81 globular cluster. So which we identified, by the way, and showed in this plot as source 3. Now, this observation is bizarre, and mainly because if you believe that repeating FRBs are produced by young magnetars that are mainly formed by prompt formation channels like type 2 supernovae, superluminous supernovae, and so on, we do not expect those progenitors to be found in such an old stellar system, as plain as that. So, so this discovery actually opens up a new sort of pathway to actually think about FRB origin, that whether they are actually could be possibly originated by delayed formation channels. And I also want to make it clear that another reason why low DM FRBs are really important or sort of interesting candidate is because this kind of analysis is not possible for any FRB. For example, Hubble is barely sensitive to basically detect a globular cluster at a distance of 30 megaparsec. So here in this case, we identified a globular cluster because it is so nearby, 3.6 megaparsec. Now, so let me talk about another localization, local universe FRB localization that sort of satisfies the later criteria. Now, this FRB 2018-1030A was discovered back in 2018 by the CHIME FRB collaboration. And we made in the discovery paper an interesting fact about this FRB is that the DM excess is quite small. So we expected that, that this FRB has a nearby host. And if you remove the Milky Way disk and halo contribution, using some fiducial models or some fiducial values, you got the DM excess of only around 20 to 30 units. And that means we expect the FRB to be nearby. And that's what we found. So we localized this FRB. So recently, actually I forgot to show you that. So on the right-hand side, you can see baseband plots, baseband localization plots for the 4 bursts that we have detected for this specific FRB. And using them, we're actually able to localize this FRB to a sky area of around 5.3 arc-minute square. So in this plot, I've shown the 90% confidence localization region of the FRB as sine ellipse. And now with this localization, the galaxy that almost instantly takes your attention is NGC 3252. It's a spiral star-forming galaxy located at a distance of 20 megaparsec within our supercluster, Laniakea. And that's amazing. And in fact, when we estimate the chance coincidence probability for this FRB, for this galaxy to be the host of this FRB, we found that the chance coincidence probability is very small. It's less than 0.25%, even after accounting for the look elsewhere effect. Like CHIME is detecting many FRBs. So it should be counted while estimating the chance coincidence probability. Now, independent to this low chance coincidence probability, we also identify all the plausible galaxies that are there within the FRB localization, and which if exist at the maximum estimated redshift for this FRB, which is around 0.05, it would be at least 5 times fainter than the faintest FRB host discovered today, which is FRB 121102. And we estimate the spectroscopic redshift for all those galaxies. So these galaxies are shown as boxes here. And for all the galaxies except NGC 3252, we found the redshift, spectroscopic redshift, significantly larger than 0.2, basically. So that both these analyses strongly support the association of this FRB with NGC 3252. Now here I basically showed the fitted spectral energy distribution of NGC 3252, which is similar, which is typical of a star-forming galaxy. And we use this modeled SED to estimate different physical properties of NGC, of this galaxy. And I strongly refer you to the paper that will be soon put on the archive to read more about that. Now, you may ask, what are the implications? Now, and there are definitely a few important implications for this localization. The first one is we estimated the Milky Way halo contribution along this FRB sight line. And as I said, low DM FRBs are perhaps the best candidates to constrain the Milky Way halo contribution. And we found it to be smaller than a few models. More on this will be discussed, I think Amanda will discuss in her plenary talk, I think on the second last day of this conference. And second, so using the 3 local universe FRBs that were, by the way, all of them were detected by CHIME FRBs, we estimated a lower limit on the volumetric rate of less luminous FRBs and found it to be at least 100 times larger than the core collapse supernovae rate, the most common channel to form compact objects, which also suggests that low luminosity FRBs are more likely to be repeating sources. And lastly, based on the observed co-moving number density of repeating FRBs. So we argued in the paper that it is unlikely that all repeating FRBs are produced by young, means millisecond magnetars with age less than 100 or 1,000 years, which are sort of formed or proposed to form via cataclysmic events like superluminous supernovae, long and short gamma ray bursts, or even as a remnant of accretion-induced collapse of a white dwarf. So therefore, if you include them, so we actually need a more dominant mechanism to produce repeating FRBs, even if we include them as plausible formation channels. Now here I basically showed all the 6 localized hosts of repeating FRBs on the mass.
3 minutes remaining, Mohit. Sorry to interrupt.
Thank you very much, Shivani. Now, repeating FRBs on the mass versus star formation weight plot, where in the background, I basically plotted star forming galaxies identified in the SDSS DR4 catalog. And it is interesting to know that all the repeating FRBs are either irregular or spiral galaxies. And most of them are close to the star forming main sequence, except these 2. This one, the host of R3 or FRB 2018 or 916b, and M81, now which are more likely Green Valley galaxies, galaxies that are transiting to a more quiescent state. Now, you may say that, well, M81 repeater is localized to a globular cluster, so how it fits in this main sequence thing, which is absolutely right. And that's why we need a larger sample of FRB hosts to actually say something meaningful about the repeating FRB population. Last but not least, it is nice to see that local universe CHIME FRBs is filling the phase space between FRBs and galactic pulsars. And as you can see in this plot, originally taken from Nemo et al. So on the x-axis, it's the transient duration, y-axis is spectral luminosity. You can see that M81 FRB and R4 is actually have lower spectral luminosity compared to this whole bunch of low FRBs localized to higher redshifts. And so even better, it shows that the low DM FRBs have the potential of checking if there exists a low luminosity cutoff for these FRBs, which is another promising way to constrain different FRB emission mechanisms. Now, with that, here is my summary slide. And now I would like to take questions. Thank you very much, everyone, for your interest and attention.
Thanks, Mohit. Do you have questions for Mohit?
Oh, I see my videos off. Great.
You have a nice background.
Thanks. I didn't realize my video was off. Sorry.
We have time for some questions. Are there questions for Mohit? We got one from Matthew. I'm assuming that the host can't contribute much DM in the second guy.
Thank you very much, Matthew, for this question. Yeah, because the DM access in this case is it's just 20 or 30 units, as I discussed. So we expect the DM contribution for this host would be around 30 or 40 units. But you can see it's an edge-on galaxy, and there are like these bright spots. I cannot show you the image. So these bright spots are actually H2 regions. So there are H2 regions even at the edge of this galaxy. So yeah, it's possible that the host contribution is low, and FRBs may be associated with one of these H2 regions.
Then follow-up question, Matthew says, so is it in a globular cluster too?
That's a superb question, Matthew. I think I should wait for the event collaboration to localize this source as well. And then we can just use Hubble and see whether there is a globular cluster at that location.
And do you have any more low DM FRB hosts in your bags that are yet to be published?
Yes, there are a few, and stay tuned for that bag to be open and put on archive.
Cool. We still have time for a few questions. Are there more questions? Final call for questions. Okay, if not, we'll thank Mohit and we'll thank all the speakers in this session. It's me clapping on behalf of 81 attendees. That's good. So this concludes our session on populations. And the next in the timetable is the PhD and postdoc mingle session, and that will be happening in the Gather Town. So in the same PDF where you found the link for these plenary session, there is a link for the Gather Town as well. So we'll meet you there. Thanks for joining us and have a lovely day. Thanks.